All right, so I've made a basic LR circuit with a special kind of switch. This is called a make before break switch. So an inductor, as we've kind of talked about, is a current device, unlike a capacitor, which is a charge device. Capacitors store their energy based on how much charge has been stored on the capacitor. An inductor stores its energy based on how much current is passing through the inductor. In fact, it's basically IL squared, where it's the current passing through the inductor times the inductance squared. And we'll get to proving that later, so that I don't want you to worry about that today, but if there's current passing through an inductor, it's storing energy. That's the whole deal. But in order for you to utilize that energy, you can't disconnect the conductor from the EMF. The moment you do, you have an immediate loss of current because there has to be a complete circuit. So if you want to harness the energy that's inside an inductor, you need to be able to make sure the current stays passing through the inductor while you're attempting to use the energy in the inductor. A capacitor, we could just separate the capacitor from the circuit, move it someplace else. The charge stayed on the capacitor. So once you disconnected the capacitor from the circuit, it remained holding energy. But an inductor only has energy in it when current is passing through it. So in a make before break switch, which is symbolized here, the connection to the new part of the circuit is made before the connection to the old part of the circuit is released. So I kind of drew that B in the wrong spot. So let me move that dot and put that B is right here. So in this circuit, if I say the circuit is connected to A, then we have a pathway that leads like that through the circuit. If, however, I say we're going to throw the switch to B, then the connection to the circuit that goes through B is made before the connection to the circuit that goes through A is lost. That will turn into a circuit like this, and will allow the current to remain passing through the inductor while you're setting the switch. It's called a make before break switch. So when you're looking or when you're reading an FRQ and they bring up the idea of a make before break switch, they are telling you that the current will remain passing through your inductor while your switch is changed. Now, we had a hard time with this yesterday, and I blame myself completely. It's all my fault. But we were supposed to come up with I as a function of T across our inductor. And I don't know that we did a good job of that. And perhaps we should look back into that. But instead, I've just written out the steps, and I will post those for you guys to go through them. But it looks like this. Where this is the EMF, that's the inductance, and that's the resistance. It's really similar to the voltage across the capacitor of a capacitance switch as it builds up. The difference, of course, is that at time equals 0, the current in our circuit is 0, and at I equals infinity, the current in our circuit is whatever the current would be as if the inductor were not there and had 0 resistance. That's the basics for an inductor circuit. It works the opposite of a capacitor circuit. In the capacitor circuit, the current is maximum while the capacitor is charging and then decays over time as the capacitor gains more charge. In an inductor circuit, the moment you attempt to connect the circuit, there's a back EMF that prevents the flow of any current at all. But that goes away over time. So the more current you build up, the more current that's passing through the circuit, the less fast the current has to increase, but will eventually reach a maximum as if the inductor wasn't there. Now, what this is going to mean for our circuits is that an inductor is a switch in the same way that a capacitor was a switch. The capacitor allowed for the gradual reduction of current over time, while this circuit allows for the gradual increase of current over time. So when you first turn the switch on, the inductor doesn't allow current to pass. Let's start with that. This is how an inductor is different than a capacitor. At time 0, when you first throw the switch, the inductor has infinite resistance. I'll give you a second to think about maybe writing that down. Using the word charge is probably the wrong word to use here. So when there's no current passing through an inductor and you first connect it to a circuit with an EMF, in that state, the inductor appears to have infinite resistance. And in the long term, in the steady state condition, an inductor appears to have zero resistance. It behaves the opposite of a capacitor. Right? In the uncharged state, a capacitor appears to have zero resistance. In a fully charged state, a capacitor appears to have infinite resistance. So this circuit behaves in the opposite manner. In a make before break circuit, you get the opportunity to use the energy that's stored in an inductor in the same way that in a standard capacitor circuit, you could use the energy stored in a capacitor. So clearly, if we put the switch to A and allow it to sit there for a long time, our current will build up until we reach this maximum current. If we throw the switch to B, we still have the energy in the inductor. Under that circumstance, that energy will slowly pass through the capacitor. What's happening is pretty straightforward here. When we first throw the switch to A, there's no magnetic field in the inductor. When you first throw the switch to A, there's no magnetic field in the inductor. Current starts to build up. And as the current attempts to push through the inductor, there's a change in the flux to the inductor. Due to Faraday's law, that produces a back EMF in this direction to try and prevent the flow of those charges. But the more current you get, the less that back EMF affects the circuit. In the steady state condition, that back EMF goes all the way to zero. And at zero, you get full passing of current through your circuit. Now, we're going to have the same problem. When we flip the switch to B, and suddenly we have current passing through the inductor in this direction, but no applied EMF, there's going to be an attempt for the magnetic field to change, causing a new EMF in the circuit. Under those conditions, the inductor will push current through the circuit as the magnetic field collapses. That collapsing magnetic field drives an EMF to push the charges through that resistor. So it stores energy in a slight different way. A capacitor stores the energy in the electric field. An inductor stores the energy in the magnetic field. That's the difference. So as the electric field collapsed, it would push charges to allow those charges to return to their natural state and equalize. That's how a capacitor operated. In an inductor circuit, the magnetic field collapses, pushing the charges through the circuit using Faraday's law. In both cases, the energy is stored in the device and can be extracted upon setting the circuit up correctly. Again, the biggest difference between a capacitor circuit and an inductor circuit is that you have to maintain the current in the inductor for the energy to be there. With a capacitor, you can kind of store that energy for a long period of time. So, because I think this is pretty easy and will help with an understanding of how these circuits behave. Okay. Basic parallel circuit. Everybody see it okay? All right. And since there's so few of you here, this will be easy for me to pick on folks. We're going to throw the switch. The closing of the switch is time zero. What's the current through both resistors at t equals 0? Employ what you just wrote down. You shouldn't need a calculator. No. There are two resistors here. At time equals 0, is the inductor have current passing through it or not? No. If there's no current in the inductor and you connect an EMF to the inductor, what is the resistance of the inductor at time 0? Infinite. So this becomes a resistance of infinity at time 0, the moment we close the switch. Can any current pass through this leg of the circuit? No, which means all of the current is going to pass through this leg of the circuit. I would assume it'd be 2 amps, yeah. Right, we just use Ohm's law. 12 volts across that 6 ohms, 2 amps. So, at t equals 0, the 6 ohm resistor sees 2 amps, and the 3 ohm resistor sees 0 amps. So, of course, B is going to ask, what happens at the steady state condition? Is there any change to any of the resistors at the steady state condition?
Yes.
Which one? Do they both change, or just one changes? None of them change? Are you sure? All right. So you said they're both going to change. I think you're wrong. I think the voltage across the 6 ohm resistor stays 12 volts, which means it continuously still pulls 2 amps. I don't think anything changes about that resistor. Right? It's a parallel circuit. They each are connected directly to that 12 volt power supply. But in the steady state condition, when we get the full current passing through this side, the inductor appears to have a resistance of 0, which means we will grow to have a current in the 3 ohm resistor. How many amps, by the way?
4 amps.
4 amps. Right? There'll be 12 volts across this resistor, making this 4 amps. Again, an inductor behaves in the opposite manner of a capacitor. In the capacitor circuit, we get the reverse situation in which the capacitor has a resistance of 0 at time 0 and a resistance of infinity in the steady state condition. The inductor circuit behaves the opposite. Let's try that again. Let's go with 12 volts again. Let's go with 2 ohms, 6 ohms, and 3 ohms. And this will be our 1 Henry inductor. All right, I'm asking the same question. A, what is the current through all the resistors? Assume t equals 0 is the moment the switch is closed again. All right? You try it. Talk to your neighbor. I'm going to go around and see what you guys get. So, in the good old days of us talking about this, if you remember what we did to get us thinking about these things, is we looked at the circuit and created a small version of what the circuit was like for each of the 2 conditions. And we're not caring what happens in the middle. We're just caring about the transitional part. So at t equals 0, the resistance of this portion of the circuit is infinity. That wipes out that entire leg, right? Because no current can pass through this portion of the circuit if the inductor has infinite resistance. So the t equals 0 circuit is just this. This is the t equals 0 circuit. Both resistors are going to see the same current. 12 eighths, or what, 4/3 of an amp?
3 halves.
Okay, 3 halves. Yes. I'll math better later. In the steady state condition, it's as if the resistor or the inductor isn't in the circuit at all. 2 ohms, 6 ohms, 3 ohms, 12 volts. right? You may need to do stepwise reduction. And if you don't remember how to do this, taking your two resistors that are in parallel, replacing them with an equivalent resistance, and so on and so forth. You guys remember how to do that? Prove it. I'm going to come by. I want to see. Because I don't believe that you all do remember how to do that. Progress here. So you got 3 amps, 2 amps, and 1 amp. All good? Do you guys see what I mean by the inductor and the capacitor have a similar feature? They just operate in reverse. There are some subtle differences, but it's basically the same idea. The thing you have to recognize about these devices is that they do have this kind of tandemness to them, in that they provide you a way to selectively move current around your circuit and to adjust it over time. I hope that you recognize that an inductor in line with your circuit protects the circuit from a spike in current. Do you guys see why that might be beneficial? Especially if you have a device that is current sensitive. So believe it or not, a lot of electronics will have an inductor in line with their power supply, so that when you turn it on, you don't just spike the circuit with a whole huge amount of current right at once. It allows the current to build up over a small period of time so that the current reaches its maximum, maybe when the thing is warmed up and able to do so. Have you ever turned something on and you hear a clicking noise before the power comes on? That's generally a relay, but a relay is just another form of an inductor or an inductive switch that allows the ramping up of current. Now, it does that in the reverse too, because when you switch off a circuit with an inductor, the inductor has to dissipate its energy over time. This allows for you to allow the current to drop off in the same manner. In fact, that's the thing we should do right now. I want you to imagine a discharge circuit in the same manner that we started a moment ago. So we'll have our make before break switch. What was that?
Sorry, I screwed up the stepwise and I'm trying to figure out how.
Do you need me to go back and do your stepwise reduction?
No.
The 6 and the 3 are in parallel. They reduce to 2 ohms. 1/6 plus 1/3. Inverted.
Then you flopped it.
Do I have to keep going?
No, I just said it was half an ohm.
You said it was half an ohm.
I didn't forget to flip it.
It happens. All right, back to the circuit. When we set the switch to A, the circuit charges up. This was the charging circuit we talked about yesterday. We know that at the steady state condition, the long-term condition, when the inductor presents no resistance to the circuit, at that moment, the current passing through the resistor and the inductor will be based on Ohm's law. This is the max current in the circuit. And at that moment, the current is passing this way through the circuit. All good? So we throw the switch at a new time equals 0 from A to B. This cuts out the power supply and makes this your only loop in the circuit. Now, at time equals 0, the current in the circuit is epsilon over R. Make a differential equation that could be used to find the current as a function of time, just in the loop that's shown. And I'm seeing a voltage drop across a resistor minus a voltage drop across an inductor. That has to be equal to 0. Just 2 elements here. We've cut out the battery. So it's still going to be minus IR minus LdIdt. Still Kirchhoff's laws. So there, you've created a differential equation that could be used to solve for the current as a function of time. So that's it. The inductor is pretty easy because the differential is built into the definition of the voltage drop across the element. It's not like charge where in current where you had to put in dq/dt for the current. This one is very straightforward because you already have your differential as a part of your definition for voltage. Now all you have to do is split the derivative. You can do that too. I would expect you to be able to do that. And I expect it to take like 60 seconds. But remember your boundary conditions. At time equals 0, the current is epsilon over R. So you have a boundary condition to employ. I mean, let me back up. Did anybody not understand where this came from? I'll try and explain it, but it's just one loop. As Kirchhoff's rules go, this one's pretty meager.
Why are they both negative? I thought that like the current in this two, like in one loop has to pull like the current addition, or the voltage is
All circuit elements act as a voltage drop unless they're an active battery. Or the other way to describe that is in the direction of our current, these elements use voltage. Does that make sense? Because we went the other way across the battery, it too would be negative. But they represent a reduction in potential as you go across them. So from here to here, there's a reduction in potential, and from here to here, there's a reduction in potential. Okay? Not to mention, in fact, if you don't do it this way, you run the math, you'll find exponential growth in your current, and I don't think that's going to happen, right?
yeah, because it won't be that negative.
Right, so you need that negative sign in order for it to mathematically make sense. Yep?
If the inductor is providing an EMF, why aren't we like representing that?
So, did you hear any of the words I just said? Because that was her exact question. But it's not providing an EMF. That's not what it's doing. It's not an active device in that manner. In the same way that the capacitor doesn't provide an EMF. It provides a separation of charge through an electric field that's stored in the capacitor that can push charges to allow them to equalize. But you still treat it as a voltage drop as a circuit element. Yeah. So, are we all okay here? Now, the math is easy. This is as straightforward as it's going to get. So, I should be able to see the math on your papers, right? Take a quick little walk around, see a little bit of a calculus work, except for like the 4 people who aren't doing it. So, let me. All right, so we start this by isolating the differential. So, I'll have negative R over L times I equals di dt. That okay? Everybody see where I'm starting? All right. Split the derivative. Collect terms. Take the integral. Choose your limits. Find the antiderivative and apply your limits. I think I need to reverse those though. Yeah. Sorry. Collect the natural logs and raise them to a base e. Solve for I. Decaying exponential that starts at whatever the current was at time equals 0 and goes to 0 at infinity. Other little things here, like, is it clear to you that the time value for an inductor is a little different than the time value for a capacitor, and that the other one was RC and this one is going to be L over R? Yeah.
Can you explain how you got the limits for the current integral?
Yeah. At time 0, what was the current going through the inductor? Right? It had been connected to this EMF when the switch was at A. So when we flipped the switch, that current was still epsilon over R. Right?
Yeah.
So when we set our limits here, at time 0, which is when we flipped the switch from A to B, the current in the inductor was the Ohm's law current from the circuit.
I thought when we flipped the switch, oh wait, it was already charged.
Right, had full current running through it.
Yeah.
So, but we still have I at some future point in time and T at some future point in time. Right, that's why our top limits are always going to be I and T or Q and T or whatever. Is that okay?
Yes. If you had it like charging, then would you put 0 for I?
Yes. But that would be the charging circuit, which would have been this. And I tried to do it as a indefinite day before yesterday, and that just failed. We only have 1 minute, so I would not be able to do this one again. But if you wanted to do it again, when you get to the point where you have your integral at t equals 0, the current would be 0 through your inductor. And then you set your upper limits to be I and T.